Okay, I think we're on, right?
Yes.
Okay. So hello everyone. Today we have Dhruv Rohatgi with us. So for those of you who've been following the seminars, you probably saw him for the last season, where he was also presenting one of his papers. But for those of you that are new, Dhruv is a PhD student at MIT. He's broadly interested in theoretical machine learning, and he's done tons of amazing works in reinforcement learning. He's advised by Anko Moitra, supported by various fellowships. And today he's going to tell us about one of his code papers, which is about imitation learning, or more specifically, next token prediction and the various trade-offs there. So I think it's a really nice paper. I'm really looking forward for the presentation. So Dhruv, thank you for accepting the invitation, and you can go ahead.
Cool. So yeah, thanks for the introduction, and thank you all for coming. So this is based on joint work with Adam Block, Audrey Wang, Akshay Krishnamurthy, and Dylan Foster. The broad motivation for this paper is an empirical phenomenon known as error amplification, which has showed up in two apparently different domains. One of them is offline imitation learning, and one of them is autoregressive language modeling. So in offline imitation learning, you want to train, for example, a robot to perform some task, and you have expert rollouts, expert trajectories. So you just train the robot to imitate these trajectories via some algorithms such as behavior cloning. And it has been observed many times that when you use behavior cloning, the trained the trained policy, when you try to execute it, will often drift to worse and worse states over time. And this is sort of what we call error amplification. Now, in autoregressive language modeling, you have some language model that you train, for example, on the internet, on text data. And you train it via next token prediction, which I'll explain later what it is if you're not familiar. But it's been observed that language models trained in this fashion, when you try to generate text from them in the naive autoregressive manner, they often lose coherence as the generation length increases. So in both of these domains, there's been a lot of work in trying to mitigate this amplification by algorithmic modifications. So in imitation learning, one very popular technique is to use online access. So if you can interact with your environment, if you can send your robot out into the environment and collect new data with new policies, you can perform online imitation learning. And methods such as Dagger have been observed to mitigate this amplification. There's also various offline strategies based on, for example, data augmentation. And in language modeling, there's various strategies based on inference time mitigation. So instead of just autoregressively sampling naively from your language model, you might do something more sophisticated, such as nucleus sampling. Now, in this talk, we're interested in sort of zooming out a little bit. So we're not going to consider online imitation learning. We'll focus strictly on the offline settings. And we want to zoom out from specific algorithms and ask, what are the fundamental statistical and computational sources of error amplification? And if we choose our algorithms more cleverly, can we possibly avoid this amplification? So there has been some work recently on statistical origins of error amplification in offline imitation learning. And they take the vantage point of understanding how the sample complexity depends on the horizon of the problem. So the idea is that if you need more samples to achieve the same error, then with the same number of samples, you would be incurring worse error. And this is sort of the instantiation of error amplification. But this is in well-specified theoretical settings. So this is in settings where the expert policy that you're trying to imitate lies in the policy class that you are optimizing over. So the only source of error is statistical error. However, often in applications, there is going to be some fundamental misspecification, meaning that the expert policy will not actually lie in your model class, in your policy class. In imitation learning, this can arise if the expert has some privileged information. So the expert is using some information about the environment that we would like our trained policy to not use. In language modeling, this can occur because we are trying to imitate some extremely complex distribution, such as all text on the internet, and our model only has some limited capacity. So in both these settings, there has been some empirical work that posits that misspecification is a source of error amplification for the algorithms that people actually use. And of course, this raises the question, if we're willing to consider more sophisticated algorithms, how fundamental is error amplification, and to what extent can we avoid it? Okay, so that's the broad motivation. Now, the quick organization of the talk. I'll start by giving some formal definitions of imitation learning and sequence modeling. And in particular, I'll show how you can think of sequence modeling as essentially a special case of offline imitation learning. And you can think of the standard algorithm for sequence modeling, namely next token prediction, as a special case of behavior cloning. I'll then focus on sequence modeling. We'll talk about how we can quantify error amplification in terms of a theoretical setup for agnostic distribution learning. And that's it for definitions. Then we'll talk about failure modes of the standard algorithm, log-loss next token prediction. So why is it not the gold standard? And then finally, in the bulk of the talk, we'll talk about how can we avoid these failures? Can we avoid them statistically? And then can we avoid them when we're restricting focus to efficient algorithms? So that's the broad overview. And the gist is going to be that some improvements are possible, but there is a fundamental computational barrier. Okay, so definitions. If you're not familiar, offline imitation learning basically has a similar setup to reinforcement learning. We have a Markov decision process with some state space, action space, and horizon. The difference is that the reward function is unknown, and we have access to rollouts from some expert policy pi star. So our goal here is the same as the reinforcement learning goal a priori. We just want to maximize reward. But because we don't see the reward, you might ask how this is possible. The ansatz is that it suffices to imitate the expert. So if we can learn the distribution of the expert policy pi star, then we can approximately maximize reward. And so from sort of the statistical perspective, this motivates saying, okay, let's look at the distribution learning version of imitation learning, where we would like to produce a policy pi hat such that the trajectory distribution induced by pi hat, that's what I mean by p pi hat, is close to the trajectory distribution induced by pi star, which we're getting samples from. And here, this distribution error measure h squared is the squared Hellinger distance. If you're not familiar with it, you can think of total variation distance, and the takeaways of this talk will be roughly the same. It's just sort of cleaner to work with. And one other point of notation, I'm going to just use the notation pi star to refer to the trajectory distribution induced by pi star, just because it's a little bit cleaner. But throughout this talk, our error metric is in terms of error in the trajectories induced by different policies. Okay, so this is a fine setup if pi star is some simple policy that we can hope to get very, very arbitrarily close to. Of course, in the setup we're interested in, there is some misspecification. So to formalize this, we need to introduce some policy class pi. This is the class of policies that we are optimizing over, and we do not assume that pi star lies in this policy class. So now we cannot hope to approximate pi star arbitrarily well if we're computing a policy pi hat in this class. Instead, what we hope to do, and this is essentially the same as agnostic distribution learning, is we hope to compete with the best in class. So that's this min h squared pi star to pi. That's the best in class Hellinger error from pi star to our policy class. And our goal is to compete with this up to some additive statistical error, epsilon stat, which we would like to go to 0 as the number of samples goes to infinity, and also some approximation factor, CAPX. And the CAPX is how we quantify error amplification. So we say that if it's constant, which is sort of the best case, then there's really no error amplification happening. We're doing about as good as we possibly can. But on the other hand, if CAPX grows with problem parameters, then we see that there is error amplification, and this is sort of the bad case. And now I want to remark here that most theoretical works are considering well-specified setting, so the only error is this epsilon stat. But for our purposes, we are most interested in CAPX. And as long as the statistical error is somewhat small, we're basically happy. Okay, so that's the goal for imitation learning. What is the algorithm that people typically use? The algorithm they typically use is behavior cloning. Now, one version of behavior cloning is behavior cloning with the log loss, where you look at all your data and you maximize log likelihood of each action conditioned on the previous state. And there's a couple other variants of behavior cloning that you could introduce. For example, some people in practice, sometimes you would do behavior cloning where you're minimizing some geometric error. We're going to focus on behavior cloning with the log loss because in the well-specified setting, it has sort of the best sample complexity guarantees. It's sort of a clean theoretical testbed. But I think a lot of the lower bounds we'll discuss should also apply to these other versions of behavior cloning. Okay, so empirically, behavior cloning often suffers from error amplification. And there is some evidence, both theoretical and empirical, that this should not occur in well-specified settings, at least if you're using the log loss. So in some sense, it seems like the error amplification is indeed due to misspecification here. And later we'll discuss how this shows up theoretically. Okay, now let me turn from imitation learning over to sequence modeling. So here we have some context space X. You can think of this as the space of prompts that you ask your language model to answer. We have some distribution mu over prompts. We have some token space A, and we have some horizon H. And we also have some model class pi, which consists of models, which are maps from contexts to distributions over sequences of H tokens. And in sequence modeling, we are given IID samples. Each sample consists of a context and a sequence, X and A1 through H, where A1 through H is drawn from some model pi star conditioned on the context. And our goal is to learn this conditional distribution pi star. Now, because we're thinking of the misspecified setting, our more specific goal is going to be to learn in Hellinger distance and compete with the best-in-class Hellinger error. So again here, we try to compete with the min over all models in our class of the Hellinger error between the induced distributions of pi star and the model in the class. Yeah, question?
Yeah. Can I ask a question?
Yes.
Quick? Do you hear me? Hello?
Yes, yes.
Whoa, I cannot hear you. Oh, wait, that's my end. Okay. Something happened to, yeah, like where the sound went, it went to the speaker in some other room, I think, for a while. Yeah, like Hellinger distance. We love it. It's great. Why specifically the Hellinger distance?
Yeah, so I mean, like, I think that you could do basically the whole paper in total variation distance, and like qualitatively speaking, the bounds would be like pretty similar. Like you would change the rates. Your h's might become like square root h's because you have to do some conversions, but like qualitatively, I think the results would be similar. There are some arguments you can give that Hellinger gives like slightly tighter bounds in some cases, but you can look at Dylan's previous paper on well-specified imitation learning if you're curious about that. But I don't view the difference as particularly important.
Right. I guess maybe for downstream tasks, like if it was actually reward maximization that you wanted to do, this is not bad either.
Yeah, I mean, they're quadratically equivalent.
Oh, what do you mean by that?
Like you can bound Hellinger by, like you can upper bound it by total variation and lower bounded by total variation
Oh
squared.
no, actually, I'm talking about the reward. Like if you have some downstream task and you just care about whether you solve the task, you don't really care about what way you solve the task or whatnot. You can still relate. If you're doing well on Hellinger, then you're
Yes.
gonna do well on downstream tasks like that. Like
Yeah, you can do that
so
because
that can
total
be.
variation bounds like supreme over all bounded reward functions.
The only thing is that maybe it's going to demand a little bit too much if you have some downstream task, because you're required to copy exactly like what the policy generating the data is, and maybe that's not really required. But
Yes.
fine.
Yeah, so you can, like, if you have some structural prior on your reward function, then definitely like you should be doing something
Maybe
different.
using that.
But
Mhm.
it's not clear like if we've converged to the right theory for that sort of like inverse RL type stuff.
Okay. Cool.
Question?
Cool.
Yeah.
Yeah, maybe I have a similar question. If instead of a statistical divergence notion, we were considering the suboptimality with respect to the reward of the environment,
Yes.
and there instead of the minimum divergence, we would have the minimum suboptimality that can be achieved in class, would we still suffer error amplification or not? Do you have any insight about that?
Ooh, I mean, okay, if you're trying to if you want to change the right hand side to be minimum suboptimality, then I would be kind of worried, because you could have some policy with low suboptimality that's just like nothing like pi star, right?
Yeah, basically they would achieve similar reward even if they could take action in very different way, but
Yeah, and then it's not clear what pi star is buying you. Like if
yeah, maybe
so, like you could change the left hand side for sure and ask if you can get better bounds. I don't know if you could change the right hand side.
Okay, thanks. Sounds interesting.
Yeah, but it's a good questions. Okay, so yeah.
Ayush.
Hey, I have a quick question as well. So if you change the objective to be like best in class, so instead of trying to be close to pi star, you somehow want to be close to best in the model class.
Best in what sense? Wait, Ayush.
Oh wait, can you hear me?
Best in what sense?
Like if in the reward setting, like best in the
okay.
yeah. So okay, like this question roots from what does the statistical epsilon stat depend on? Like, does it depend on like is it simple? Like yeah, what is this epsilon stat for your case?
Like standard algorithms will get like log pi over n or something.
Log pi.
Log size of policy class all divided by n.
I see. And then like it's not clear what to do if you just want to compete with best in class, right?
I mean, if your best in class is sort of similar to pi star, then I'm not sure if there's a distinction really. Like your best in class and pi star are like sort of epsilon apart, and you're worried about being like much more than epsilon off, I think. But I don't know, maybe.
But yeah, I think I'll follow up later.
Yeah, maybe at the end we can see.
Yep.
Okay, so as most of you are probably familiar, in sequence modeling, the basic ansatz is to learn conditional distributions token by token. So we know that any model can be represented in terms of h different token level conditional distributions. And moreover, if you have these conditional distributions that you can sample from conditionally, then you can sample from the entire sequence model. And finally, as I mentioned, any model you can also think of in terms of the joint distribution that it induces on a context and a completion drawn from that model. And throughout this talk, I'm sort of going to be going back and forth between all these different notions of a model as a sequence level distribution versus a model as a sequence of token level distributions versus a model as sort of a joint distribution. So motivated by the autoregressive interpretation of sequence models, the natural algorithm that you would think of and that people like to use is next token prediction. In particular, next token prediction with the log loss learns to maximize the log likelihood over your data of each token conditioned on the context and the previous H-1 tokens for that sample. So this is basically the cornerstone of language model pre-training. And it also has some nice theoretical foundations because it's equivalent to maximum likelihood estimation over this family of joint distributions over sequences. Unfortunately, there's this issue we mentioned of error amplification. When you try to naively generate samples from your trained model, you sort of get some sort of compounding over the horizon. And so again, this motivates the question of like, can you do better? So before I get there, let me make one final definitional remark, which is that I've stated these two problems somewhat independently, but in fact, you can interpret sequence modeling as a special case of imitation learning. So the setup here is that you can think of the autoregressive MDP, where you have some you have some context and some tokens, and your action space is the set of the token space, and the transition dynamics for this MDP are deterministic. So if you're in some state which has some sequence of tokens, and you take some action which is one new token, then you transition to the new state, which is just concatenates the state in action. And it's not too hard to see that offline imitation learning, as we have set it up, with this autoregressive MDP, is precisely autoregressive sequence modeling, because policies are just sequence models, and behavior cloning actually specifies to next token prediction. So for the rest of this talk, sort of for cleanliness, I will specify everything to the sequence modeling setting. However, the majority of our results generalize. So all the lower bounds also apply to imitation learning, just because sequence modeling is a special case. And some of the algorithms, but not all of them, will also generalize. And so this is our question. Yeah.
Yeah, can I ask a question? So it seems that the whole thing is boiling down to maximum likelihood estimation in a specific model family.
What whole thing? So I mean, like that's
yeah, like your goal is or the algorithm, and
I'm
the
interested in like
criteria. The criteria uses Hellinger distance, but like, okay, if it was log loss, it would be roughly the same, right?
well, no. So I mean, you're asking if Hellinger versus KL, right?
I guess.
So I think like I would say KL gives somewhat worse, like misspecification in KL can be like much larger than misspecification in Hellinger, because you can have like some small chance of like corruption essentially.
Yeah. I guess what I wanted to ask is that in the classical literature on statistics, people study maximum likelihood estimation with and without misspecification.
Yes.
Do we have similar documented error amplification of the misspecification level? I sort of like people usually do get consistency, which would consistency in that case would mean that you're actually reaching the misspecification level without amplification. And I'm trying to remember what are the conditions that make that possible and why those conditions don't hold here. I guess one difference is that they would definitely just go for the log loss, which is the KL.
Yes.
But is that it, or
I think that is the fundamental difference.
Also the data is like there is zero correlation in the data here, but that shouldn't make any difference whatsoever because you have IID
That's right.
over the serially correlated data anyway, so that shouldn't make much of a difference. Okay, all right, okay, interesting.
Yeah, I guess maybe when I discuss the like failure modes, it might be more clear like why this is a little bit different.
Okay.
Yeah. So we're interested in understanding, like, if we change the algorithm from log loss, how can we mitigate this error amplification as quantified by this approximation ratio? and what are sort of the barriers if we want to do this efficiently. So to start this, we need to discuss why log loss prediction is not like already solving our task. So we need to discuss how it fails. Now, in the well-specified setting, it does not actually fail. So in the well-specified setting, you get Hellinger error bound. There's just log size of policy class divided by n, and it's not your number of samples. And this is nice because it's horizon independent. So if you convert Hellinger to total variation, this implies that you get horizon independent guarantees on generation for any bounded performance measure on your like sequence generations. But this is the well-specified setting. So when there is misspecification, it's a fairly easy observation that next token prediction with the log loss can fail completely. In other words, the Hellinger of the estimated model can be a constant, even when the best-in-class Hellinger error is arbitrarily small. And the idea here is just that you could have some point, some sample, which you have some small epsilon chance of drawing from pi star. But every single model in your model class places 0 mass on this sample. And if they all place 0 mass on this sample, then all of the models have the same log likelihood, namely negative infinity. So your log loss estimator can pick anything as its output. And that's the whole proof. And intuitively, what this is telling us is that if we look at log loss itself, its approximation ratio is going to scale with some sort of density ratios between pi star and the models in our class. And this is saying that this is somehow unavoidable for this particular algorithm. Now you might ask, okay, maybe this is somewhat pathological. What if we have some sort of density ratio bounds? So here's a different failure mode. We can assume that pi star over pi is bounded for every pi in our model class, and we still get a factor of h error amplification, where the best-in-class Hellinger error is epsilon, but the error of our estimated predictor is roughly epsilon h. And the idea here is that there is a mismatch between what we are trying to our goal is, namely trajectory level error, versus our loss function, which is summing over tokens, so essentially summing over layers. And we can exploit this with the following construction. We have a model class with two models, pi and pi prime. Pi disagrees with pi star only on a very small probability mass, so a context that occurs with only probability epsilon. And so it's very close to pi star, it's epsilon close. However, we can make it incur epsilon h excess loss according to our log loss by making it disagree with pi star on every single token in the event that it disagrees at all. And on the other hand, we can define a model pi prime that disagrees with pi star on a much larger event of size epsilon h. But in the event that it disagrees with pi star only on the first token of the sequence generated, and it agrees for the rest of the tokens. So now we have the setting where both of these policies, both of these models have error epsilon h, have loss epsilon h, but one of them is a factor of h better. And so if we pick the wrong one, we suffer this factor of h error amplification. And this tells us that the log loss suffers this approximation ratio that scales with the horizon. And in a sense, the reason this is not showing up in like classical distribution learning is that we're assuming like density ratio bounds at sort of like the token level. And so at the sequence level, this translates to like much larger density ratios. But I can explain that more later. So there's one final failure mode, which I'm not going to give a construction for. It's a failure of log loss to achieve high probability. And in other words, what we can show is that if we want to achieve probability at most delta of failing, then the log loss will incur an approximation ratio that scales with 1 over delta, in addition to the previous failures. This can be avoided if you are willing to pay a horizon-dependent rate. But if you want a horizon-independent rate, horizon-independent sample complexity, then this is unavoidable for this algorithm. So again, I'm not going to give a construction for this. It's sort of similar to the previous one. But what this tells us is that we have 3 different failure modes here. That the approximation ratio of log loss depends on the failure probability, it depends on some density ratio bound, and it depends on horizon. And we can also show that these are this sort of completely characterizes the failures of log loss. So we can get a matching upper bound, where the approximation ratio scales with h log w all over delta, where w is the density ratio bound. And we can get a similar bound where you avoid the dependence on 1 over delta if you're willing to pay a horizon-dependent rate. So this is sort of standard statistical analysis. I'm not going to give any proofs here, but it's good to know. Okay, so where are we now? We've seen a couple different failure modes of the classical algorithm for sequence modeling. And now we turn to the question of how can we avoid these failures? So first, we'll show that by a classical statistical method called the row estimator, it is information theoretically possible to avoid all of these failures. You can achieve approximation ratio just order 1. But that algorithm is not very practical. So then we discuss what can we do by practical modifications to the log loss. We show that you can achieve approximation ratio sort of order h. So that's like the horizon dependence is the only dependence. But this is an inherent barrier in the sense that any next token prediction style objective necessarily incurs this horizon dependence. And this is what we call the next token prediction barrier of our title. And finally, we ask about what we can say in terms of end-to-end computational efficiency. So this is the classical theoretical CS perspective. Let's specify some concrete testbed of a model class, and let's ask what we can do in polynomial time. And we'll show that it's cryptographically hard to substantially beat the linear next token prediction barrier. But if we're willing to pay somewhat more computation, there is a smooth trade-off between computation and approximation ratio. And this is for the testbed of autoregressive linear models, which I will define later. Okay, so quick part about information-theoretic estimation. The row estimator can be defined for standard distribution learning. Nothing specific to imitation learning, nothing specific to sequence modeling. You just have some family of distributions and some data, and you compute the row estimator by solving this min-max optimization problem. Tau is some function that I've plotted here for your enjoyment. And I don't have too much intuition about why this is a good estimator, except that in some sense, it's kind of a truncation. This tau function is kind of a truncation of the negative log likelihood. So if you were to replace tau with the negative log likelihood, you would actually exactly recover the maximum likelihood estimator. But that one is like sort of unbounded, and so it doesn't satisfy as nice guarantees. This row estimator does satisfy very nice guarantees. It's sort of the best thing you could do if you want agnostic estimation in Hellinger distance. So it gets an order 1 approximation ratio, and it gets a fast rate. So that's all great. And we can even apply it to our setting of sequence modeling, just because sequence modeling is distribution learning. So we have this min-max problem. We can write our sequence model densities as products of token level densities. And information theoretically, this is solvable. And it achieves the approximation ratio order 1. So it's statistically the gold standard. Unfortunately, it's computationally unattractive because it involves min-max optimization and because you have this sort of product of density ratios. So the question that this motivates is, can we achieve similar guarantees by more practical algorithms, by algorithms that someone might plausibly want to run? So that's the next part of the talk. What could we do with algorithms that look sort of like next token prediction? So we had 3 failure modes of standard log-loss next token prediction. Yes.
I think I have a very naive question, and apologies for this very simple question. So I have a feeling like there's some conflict in the language here, in the sense that you are saying that in my right-hand side, I'll specify misspecification using Hellinger distance, but then try to look at like log loss and like this aggregated like some of these logs and stuff. But if I just specify the misspecification using, let's say, like KL or some other metric, like
Yes.
would these failure modes still happen? Like, at least from the examples, it seemed there was some incompatibility with like log versus Hellinger in the way they calculate
Exactly,
these distances
yes.
and so on. So is it all like a game of, like what you're specifying misspecification with versus like what algorithm you're analyzing?
Yes, definitely. I mean, that is in some sense like the intuition for all these proofs, like that there is a mismatch.
So
I mean,
why do we care about right-hand side being Hellinger
right.
rather than
We care about it.
Mhm.
We care about it because like if the right hand side was KL and you had some like small like fraction of corruption, for example, then you would not get like any like you would not get any like small KL. That's
Right.
basically the reason.
I see. So you're basically claiming that Hellinger is nice because it automatically captures these corruption settings.
That's right. Yeah. I mean, you are correct. Like if you look at KL, you can get like order 1 approximation ratio. You'll pay some density ratio bound in your rate, but
Exactly. That's like the standard
That's the
misspecification
standard.
analysis for behavior cloning, right? They
Yes.
pay misspecification KL and the constant is 1.
Yes.
I see. Because this row estimator seems very similar to like what would you want to do if you care about like misspecification in Hellinger, right? Like as you also mentioned with this result.
Yes.
Okay, great. Thank you.
Sure. So what we show here is that the first 2 failure modes of log loss are avoidable. So the dependence on the failure probability and the dependence on density ratios. And they're avoidable not just by the row estimator, but also by fairly practical modifications. But the third dependence on horizon is fundamental for a broad class of algorithms. Okay, so first of all, how do we mitigate the issue of failure probability? We can do a pretty simple boosting approach, where we divide up our data into log 1 over delta subsets. We apply log loss to each subset. All we ask is that we get constant chance of success for each individual subset. And if at least one of them succeeds, we're happy, because we can apply the row estimator on top of these estimated policies. So we apply the row estimator to this finite size model class, which means that it can be computed efficiently. And if any of the pi hat k's estimated by log loss are good, then the row estimator, because it's optimal statistically, it will successfully select a good pi hat. And just by working through some like turnoff bounds and stuff, you get that from our previous result for vanilla log loss, as a corollary, you get that this boosted method has approximation ratio h log w. So there's no factor of 1 over delta. And as I said, it's as practical as the vanilla log loss because you're just applying the row estimator on a small model class that can be computed efficiently. So that was one intervention. Another intervention, yes.
This seems similar to robust mean estimation or whatnot when the data becomes input to the algorithm. So it doesn't really get somehow the sub-Gaussian tail for the whole scale of data. It's just more like, you want this data is really, like, you don't like the sensitivity to the data, you can decrease sensitivity data by doing this aggregations thing. Yeah.
Yeah. I mean, there's a bunch of like very similar things, and some of them I think improve like robustness. This one somehow improves like failure probability.
But my sense is also that like, so the result looks like as if you get some nice sub-exponential tail or whatnot for the Hellinger, but you don't actually, because you have to run for every data the algorithm it's doing a different partitioning, and like you have to recompute it. It's not like that.
Oh, you're saying it
Data
depends on
policy
delta.
that
You're saying the algorithm requires knowing delta.
yeah.
Yeah, that's a good point. I haven't thought about like what you would do if you didn't know delta.
Right. So it's
Yeah.
like in this way you can reduce the data dependency in the approximation factor, but this is kind of a price that you're paying. Which, yeah, in some cases it's okay.
Yeah, that's an interesting point.
Yeah, but I think that maybe there is a fundamental trade-off as well there. That like if you wanted an algorithm that works for no matter what the data, and this data only appears with log 1 over data in the estimation error component, then maybe you can't have that.
Yeah, that could be.
Yeah.
Okay, so the second intervention that we can do to avoid the density ratio dependence, this one requires a slightly stronger access model where you have access to expert density queries. So for pi star, you can query the densities. This is sometimes going to be reasonable and sometimes not going to be reasonable. The settings where it is reasonable would be some sort of like distillation settings, but definitely not in all settings. So if you have this access, what can you do? You can take your log loss estimator, but instead of maximizing log of pi, you can maximize log of some convex combination between pi and pi star. And to analyze this, you can observe that it's equivalent to vanilla log loss on a smoothed model class where all the density ratios are now by fiat bounded by this 1 over lambda term. And so you can replace your density ratio assumption by just some density ratio factor of this lambda, which you can balance parameters to be like 1 over h times your number of samples. And you can essentially get something like h over delta as your approximation ratio, regardless of whether your initial model class satisfied the density ratio bounds. So this shows us that the first two failure modes were avoidable. And now I want to discuss how the third failure mode is somehow fundamental. So this requires a definition. What's the class of algorithms that I'm going to show incur this dependence? So I'll define something called an iterative learner. Let's fix some model class. We see an algorithm as an iterative learner if for every step little h, it's going to estimate some conditional distribution pi hat little h for token h conditioned on the previous tokens. And we like that this algorithm does not look into the future to compute this estimated conditional distribution. In other words, pi hat at step little h should only depend on previously computed pi hats and pi star restricted to the first little h tokens. So this formalizes and slightly generalizes what you would think of as a standard next token prediction algorithm, where you're sort of doing local stuff. You're not trying to like globally like learn the best model. And one thing we can notice is that this encapsulates all estimators that optimize a layer-wise loss that's summed over the like h steps, at least so long as the model class has no parameter sharing across steps. And this is sort of the most natural setting for this definition anyways. What we can show is that any iterative learner incurs an approximation ratio of horizon of h. And the policy class that we use indeed has no parameter sharing, so it's sort of it's a legitimate bound. And I'm not going to give the full proof, but I'll give some sort of like nugget of intuition for this proof. And the idea is to sort of embed this consistency game into the learning problem. So pi star will correspond to some unknown sequence z. It's a binary sequence of length h. And the game has h rounds corresponding to the learner's attempts to produce the conditional distribution at the first step, and then the second step, and then the third step, and so on. And in round little h, the learner only gets to observe the first little h tokens of z. It does not get to see the future. And it has to play some sequence yh which is a binary sequence of length capital H, same length as z. And this corresponds to pi hat at step little h. And what is the consistency condition that this learner needs to satisfy? We force the learner to output sequences that match the tokens of z that have been revealed so far. And at the end of the day, we want to minimize the number of distinct sequences that the learner has played. So what we can observe is that the optimal learner would be playing z at every single step, but it cannot do this because it does not know z, it does not know the later tokens of z ahead of time. Instead, it's going to try to guess z at the first step, and it will get the first token correct because it sees the first token, but it does not see the rest of the tokens. So it's very unlikely that its guess at the first step will be valid for later steps. And so at the end of the day, you can show that the expected number of distinct sequences the learner has to guess is going to scale linearly in the horizon. You have to keep on trying different sequences, whereas the optimal learner, which sees the future, only plays one sequence. And that's where this factor of h comes from. So this shows that for iterative learners, the factor of h approximation ratio is fundamental. In the last part of the talk, I want to talk about the theoretical CS perspective, the end-to-end computational efficiency perspective. And this is motivated by the following question. We ruled out improvements for these iterative learners, but what if you have a more clever algorithm that is still somehow computationally practical? How do we formalize this? We formalize this by asking for efficiency in some concrete setting. So we're going to consider autoregressive softmax linear models, which are defined as follows. You have some feature map phi, which maps from sequences to d-dimensional vectors. And our policy class is indexed by some convex set theta that also lives in d dimensions. And every pi theta is defined so that its conditional distribution at each step is proportional to x of theta dot phi. So essentially, at every step, we have an exponential family defined with parameter theta and sufficient statistics that's defined by the features. And our computational model is just that we can query phi, we can query the features, and we have basic access to theta, for example, some sort of projection oracle. Why is this an interesting model? Well, it's a simplification of real autoregressive sequence models where we have frozen the features. So in standard sequence models, they would look exactly the same, except that phi is also parametric and also learnable. So we've frozen the features so that the only thing that's changing is our final layer of the sequence model, sort of like the final softmax layer. And the other reason that it's a natural model is that in the well-specified setting, if we get data from a autoregressive linear model, the distribution learning task is actually end-to-end computationally tractable. And this makes these models a natural computational testbed for trying to understand the computational price of misspecification. To make this more formal, we have the following simple proposition, which says that you can implement the log loss in polynomial time using projected gradient descent. And because we have fast rates for log loss in the well-specified setting, this directly implies that distribution learning is tractable for autoregressive linear models in the well-specified setting. And this is basically a consequence of standard facts about exponential families, which tell you that the log loss is actually concave in parameter space, so gradient descent works. And also you can compute the gradients and everything efficiently. But this is in the well-specified case. What can you do in the misspecified case? Well, you could apply the same algorithm. You could apply projected gradient descent on the log loss. And we've seen that we have some bounds on the log loss for generic model classes, so we can specify them to autoregressive linear models. And so long as we have some sort of norm-bound assumptions, we can get some non-trivial competitive ratio that scales with two parameters. It scales with the horizon, and it scales with b dot, So b dot is just some sort of norm bound between the features and the parameters. And our question is, we know that we can achieve this in polynomial time. What can we achieve? Like, can we achieve anything better? Can we decrease the horizon dependence? So here's our first result, which is a lower bound. We show that if we want a polynomial time estimator in this setting that achieves substantially less than linear dependence for its approximation ratio, then we can break the learning parities with noise cryptographic assumption. A few comments here are that this shows that horizon dependence is necessary, at least for autoregressive linear models with large feature dimension. It does not rule out some sort of approximation ratio that scales polynomially in the dimension and does not scale with the horizon. And it also does not rule out learning algorithms that have access to density queries. So those are two interesting caveats that are open questions. Some quick points about how we prove this. So it's known that if you want to agnostic learn a softmax neuron, then you need to pay some norm bounds in the approximation ratio. And this is equivalent to autoregressive linear models with horizon 1 and large norm bound. And we're interested in sort of the complementary setting where the horizon is large, but we want to understand the fundamental dependence on the horizon. So we want the norm bounds to actually be quite small. So the construction was basically as follows. The expert model pi star is some noisy parity function. So the contexts are vectors, the action space is binary, and pi star is conditioned on some context, is some Bernoulli that depends on the parity function. And this is known to be hard to learn under learning parities with noise, under standard cryptographic assumptions. And so the question is just, can we show that it's very close to our autoregressive linear model class? Can we show that it has low misspecification? And they do show this. So they show that there is some polynomial interpolation method that gives you low misspecification to the class of autoregressive linear models with horizon 1 and very large norm bound. And what we want to do is sort of flip these things. We do this by defining an expert pi star, which has, instead of one strong parity observation, it has many, many independent, very weak observations. So conditioned on the context, each of these Bernoulli random variables is going to be very close to uniform, but just ever so slightly biased based on the parity function of the context. And because this pi star is much closer to uniform at every step, we can get a polynomial interpolation with a norm bound that's much smaller. And this shows the sort of misspecification bound that we need. So a bunch of details go into this, which I'm not going to go through. But that essentially proves our lower bound. And in the last few minutes, I wanted to just state this theorem, which is a Compstat trade-off, sort of complementing the lower bound. So we show that you cannot get arbitrarily good performance in polynomial time in autoregressive linear models, but you can get small wins. So we show that you can get an approximation ratio of roughly h over k for any given k, where your time complexity scales exponentially, not in h, not in d, but in k. And so if you trade off parameters appropriately, you can get some interesting trade-offs, where you get sublinear approximation ratio in sub-exponential time. And the proof is some sort of chunking argument. I'll just kind of like flash the slides for color. So there's some sort of chunking argument where you break into chunks of size k. And in each chunk of size k, you compute the row estimator using essentially a kernelization method from prior work on kernelized regression. And you do some math, and you get this result. To wrap up, what have we shown here? So we've seen that standard algorithms for sequence modeling incur error amplification. And we asked if this is avoidable. And we found that information theoretically it is avoidable. And there are some modifications to next token prediction that achieve some small advantages. But there is a fundamental barrier at a factor of h. We need a factor of h error amplification for these next token prediction methods. And then for autoregressive linear models, we saw that there is a computational lower bound, but there are some trade-offs. And the lower bounds apply to imitation learning. And some of the upper bounds apply, but not the ones for autoregressive linear models. So to wrap up, here are a few future directions. There's a couple of technical directions that I mentioned in the talk and that are stated here. There's a couple conceptual directions. One of them is that we've discussed two different notions, like proxies for computational tractability. One of them based on next token prediction iterative algorithms, and one of them based on autoregressive linear models. But for the most part, the message here was kind of negative, that if you want efficiency, you suffer this error amplification. But it would be interesting if there are somehow more permissive notions of computational tractability that allow sort of more oracles where you can get something more efficient and more statistically efficient. One other future direction is beyond offline imitation learning. What is the lay of the land? So if you allow interactive access, to what extent does this bypass the various lower bounds? And finally, most broadly, beyond additive misspecification, suppose that pi star is not actually epsilon close to your model class. Suppose that it's like somewhat far away. It's like a constant away. Are there any structural assumptions we can impose that make it still possible to learn something non-trivial? So that's all I have, and thank you all for listening.
Hey. I didn't get this additive specification avoidance.
Yeah, I guess like the most simple thing you could think of is like, what about these settings where like you have like a bunch of different experts that you're trying to imitate?
Okay.
So you have some like complex multimodal model class. You're trying to imitate with like a simple model class. Right? So you have a complex multimodal expert because it's sort of like some mixture or something. But you have like a simple model class. Like, is there any interesting model here? I've thought to some extent about this, but I don't have like great answers really.
Yeah, regarding one of the points, I guess the quantitative improvements to lower bounds, like one of the things there that I noticed is that this age dependence, when you're arguing that it has to be there, the misspecification error goes to 0 with age going to infinity, which is kind of defeats the purpose a little bit. At least they'll use the message. So I think that would be super cool to get something where you can keep the misspecification errors constant and the scale age, and still a blow up happens. One thing that should be possible, but I guess you must have thought about it.
I mean, I didn't like exhaustively try the search space. I think there's a huge search space for this sort of construction, and I did the simplest thing that works. So I think it's quite possible that there's a stronger bound. But it wasn't obvious to me.
Yeah, like not based on that construction. Yeah.
I think like maybe you need like a stochastic expert or something like that. I'm not sure.
Okay.
It also this construction also has an extremely large model class, so there's some quantitative improvements you can hope for there.
Yeah. And there is a question which is not on the slide, which is that how important do you think this misspecification error blow up is for current applications, algorithms, LLMs, whatnot? Is this the realm that we are in, or not really, or what's your feeling about it?
I think it probably depends on the domain. Like,
okay.
I think that in language modeling, like, there is something fishy happening where like people have all these fancy sampling strategies, and you kind of ask like why, like, why we need these fancy, like what these fancy sampling strategies are doing, people seem to think it's because of this sort of misspecification, like to avoid the issues that arise from misspecification. And so like you'd ask, like, can you improve the training so that like a standard sampling algorithm, a standard autoregressive sampling algorithm works?
Or maybe prove that if you use a fancy sampling strategy, then your model class, well, you kind of doing improper stuff now, but like, fine, why not?
Yeah, or prove that these are actually doing something really
Yeah,
cool,
it's actually doing something interesting.
which it's not really clear what any of these sampling strategies are doing, at least to my knowledge.
I'm like, or yeah, like whether they're doing something clever. Yeah, I guess the argmax is like sort of reasonable. Like if you're thinking about this misspecification error.
Argmax meaning greedy or what?
Yeah, the greedy something.
But greedy also does very badly, I think.
Like really?
I think very badly. I mean, it probably depends a little on domain, but I think for natural text it does badly. But I could be wrong.
Okay. Interesting.
Yeah, and the main reference I've read is this nucleus sampling paper by Holtzman and others.
I guess an obvious problem with greedy is that if you want variability, and sometimes people do that, then greedy kills that.
Yeah, but I think not just it defeats variability, but it also like leads to repetition. Like you sort of like start saying
Oh
the
yeah,
same
yeah.
things
Like
again and
yeah,
again.
that's
Stuff
true.
like that.
That's true.
So even from coherence perspective, it's not good.
Oh yeah, you can get into loops. Very cool.
Yeah.
Luca.
Yeah. I think I have a question in my mind when I was reading your paper. Like, you always define the misspecification between the state action trajectories.
Yes.
But if the environment has some structure, for example, when you use a softmax linear policy, you could assume that to be in a linear MDP or something like that. Do you think you can measure the misspecification between distribution over features? Something like that.
I mean, I think some of the simplest version of what you're asking is like in the tabular MDP setting, right? You would be measuring like visitation.
Yeah, but
Like-
now maybe not, because in the tabular setting, I guess the feature would be 1/0, and then at least in my mind of what I'm asking, the distance between state action trajectory or trajectory between feature direction visitation would boil down to be more or less the same. But
Oh, see, are you still asking trajectory level, but you measure sort of similar trajectories as like lower error because like there's similar features?
exactly, something like that.
I see.
If the trajectory, I mean, maybe exactly. If you are in an environment with a nice structure, do you think that this kind of algorithm, behavioral cloning like, can make use of the structure? Yeah, I think.
Yeah, I mean,
question in mind.
I think like probably if you have like if you're restricting to linear rewards, then somehow all you care about is these features. And I mean, you still have to have a way of aggregating the features across your trajectory. Like maybe you add them up or something. I'm not sure what's reasonable. I haven't thought about it, but it could be interesting.
Yeah, cool. I was curious to know if you thought about that or not. And another things I didn't quite get, I think, in your example on the ZK being a binary sequence and the YK trying to predicting the first bits revealed up to that point of the sequence Z. Why your final regret is the number of distinct Y sequences that you create?
Yes, I have a slide, a hidden slide that's like in a bit more detail. Like what you do is you define, like you have a huge context space, one for every sequence of length h, and you define for every you index your model class by these contexts. So for every context, you define a particular model, a particular policy, and you define that policy so that it goes wrong, it does something really bad on that particular context. And so now the number of differently indexed policies that you played at the H steps corresponds to the number of different contexts on which your policy decides, let's do something really bad.
Okay. Okay, thanks. Clever construction.
Yeah, but I guess now you can see sort of why there's like 2 to the H comes in, because you're measuring how many times you went bad out of 2 to the H different contexts.
Yeah. Maybe I can stop the recording, at least if someone of the audience wants to ask question.
But so in the row estimator upper bound,